Alright, hey guys, in this lab we're going to be talking about a simple motor controller and some basic torque speed calculations with electric DC motors. So in this lab we're going to be using a breadboard and a potentiometer along with a little metal gear motor. And a gear motor is essentially a little DC motor coupled with a gearbox. And these gearboxes can come in many different ratios. This one specifically is a 210:1 gear ratio. That means that the output shaft of the motor is quote-unquote geared down compared to when it comes out of the output shaft for the gearbox. And that means it's going to be going slower than the output to the motor. So in this lab we're going to be using these materials, and we are going to be able to control the speed that the motor is running at. And that's basically what a motor controller does. We want to be able to control how fast the motor is going, how much torque is coming out of it, etc. Alright, hey guys, so in this section I'm going to give a brief background into how electric motors behave, specifically pertaining to their speeds and their torques. So in general, simple electric motors obey a linear relationship between torque and speed. And as you can see in this graph, this is speed measured in RPM on the y-axis, and on the x-axis it's going to be torque. And that's measured in whatever units you may be using. Doesn't really matter, this is just showing the relationship between the two. So every motor has certain specifications. There's one thing that is called the no-load speed, and that means the speed that it describes the speed that the motor is running at when there's no load on the motor. So if you just plug a motor into a power supply and run it at full power, that's basically the no-load speed. Another parameter is called the stall torque, and that is when the motor has a very large load on it and it's not spinning at all. It has 0 RPM. And that is the torque that the motor is applying to resist whatever load is on the motor. So as you can see on this graph, we have the no-load speed right here. So at the no-load speed, there is essentially 0 torque being applied on the motor. And at the stall torque, it's not running at all. So it corresponds to a no-load speed or a speed of 0. And in between those two values, most motors obey a linear relationship. So most motors that you can buy online will come with a very large spec sheet. They will include the no-load speed and the stall torque. And they will also include a quote-unquote nominal operating voltage. And for the specific motor that we are using, it's supposed to be operated at 6 volts. So this linear relationship is very specific to 6 volts. Let's say hypothetically that we want to be operating our motor at a different voltage than what is provided as the nominal operating voltage. Let's say that we were given a no-load speed and given a stall torque, and these parameters were given to us at a nominal operating voltage of 6 volts. Now let's say we want to be operating our motor at 8 volts instead. There are a couple of pretty simple relationships that will help us calculate the new no-load speed and the new stall torque at this new operating voltage. So we're going to say that NO2 is our new no-load speed, and this relationship basically says that we're going to change our voltage from V1 to V2, and that is related to our original no-load speed. So in this case, we're going from 6 volts, which is our V1, to 8 volts, which is our V2. So we're just going to be multiplying our original no-load speed by 8/6, and that's going to give us our new no-load speed. And the stall torque obeys the exact same relationship. So that's going to be our new stall torque is equal to the ratio of V2 over V1 times our original stall torque at 6 volts. Graphically, this is going to look like this. We are just scaling up our operating voltage from 6 volts to 8 volts. And our new stall torque is going to be right here. And our new no load speed is going to be right here. You can see that you can scale this up. You can also scale this down. Most motors do have a minimum operating voltage, but in this lab specifically, we're not going to go into that. It's not that important. All right, guys, so let's start building our circuit. As I said before, we only have a couple components that we need. We have our potentiometer, and in this case, this is a 100 ohm potentiometer that can basically go in anywhere. And you can use the middle pin and either outer pin to make this work. So we are going to plug our positive terminal into the middle pin, and that's the one that's going to be going to the power supply. Now, let's get our motor in here. Now the other side of the potentiometer is going to go directly to the motor. So let's plug one of the motor leads into one of the outside pins of the potentiometer, and then have the other lead just go into another row, just like that. Now our grounded lead is going to go directly from the power supply to the grounded lead on the motor. All right, so that is literally all you have to do. Now we're going to be using a power source that's operating at 6 volts. And that's off the screen, so you won't be able to see it, but just know that these two leads are going to be going directly to a power source. Now, as you can see, as soon as I hooked up that positive terminal, our motor started to turn. And we have a multimeter here so that we can test the voltage across the 2 motor leads. So as you can see, we're right up against 6 volts at 5.99. So now let's start adjusting the potentiometer and see what happens to our voltage. And as you can see, as I'm turning it, the voltage is slowly decreasing. And you might be able to hear it as well. The speed of the motor is decreasing. So as we talked about earlier in the video, there's a direct relationship between the voltage that is applied between the 2 motor terminals and the speed of the motor. And we should be able to get this down pretty low. And these motors will have a certain voltage that is considered their minimal operating voltage. It will get pretty low, so we should be able to get down to like 3 volts, maybe even 2 volts with this specific motor. So I'm not going to go all the way, but you can see we're down to around 3.5 volts. It's fluctuating a little bit, but there you have it. We have a simple motor controller using a power source and potentiometer. And there you go. Alright guys, so as the last part of this lab, we're going to show you how you can estimate where you're currently operating at on our torque speed curves. So the way we're going to do that is obviously you're going to have your brush DC motor, and we made a little extension shaft here out of wood. We made this thin part is 3/8 inch wood, and this outer part was made from 1 inch diameter wood. And basically all this does is this goes directly onto the end of the output shaft on the gearbox from the motor. And what this allows us to do is measure both the rotational speed of the motor, or the output of the gearbox, and how much torque is being applied to the motor shaft. Now what we're going to do is you can mount this on, let's say, the edge of a table, and hang this part with the string off the edge of the table. And you can hang something with a known mass, let's say 1 pound, on this string and have it start in its fully outstretched position. Now, once you turn the motor on, this shaft is going to turn and it's slowly going to wind up and pull that mass up toward it. Now, you can calculate, since you know the weight of that mass, you can calculate the force that's being applied to pull it up, and you know that torque is equal to force times radius, so you know the torque that is being applied by the motor to pull that mass upwards. Now, you can also time how long it takes to move that mass from its bottom position to its top position, and from that you should be able to derive, using the radius of your axle here, you should be able to derive both the torque, like I said earlier, and the rotational speed in RPM. And from those two different things, and knowing the voltage that you're operating at using your multimeter, you should be able to pinpoint the exact location on that torque speed curve that you're currently operating at. And then you can also do things like vary the mass that's hanging on the end of the string, and you can change the setting on the potentiometer like we did before to change the voltage and see how that affects your speed. Alright, so that brings an end to this lab. Please like, comment, and subscribe our video. Let us know if you want us to do anything else, more specifically with brush DC motors or any other type of motor, and let us know what you think. Thanks.